In this video, we'll talk about partial fractions. So here, I wrote a few partial fractions that you might encounter in calculating integrals. One of them is 1 over, or whatever here, you can have any number or expression. But the bottom is made by denominators, made by products of linear equations, or linear factors. X minus a, x minus b, x minus c, x minus d. It could have 4, it could have 5, or just 2 factors. The idea is that they look this form. Well, in order to break it down, we will copy the denominator, and then at the top we would write 1 power less, which means just a constant. So a constant over x minus a plus a constant over x minus b plus a constant over x minus c, constant over x minus d, and we would go on depending on how many factors we have. If the denominator, because the numerator doesn't matter, we just had the generic one, but if the denominator is made by factors that repeat, so instead of having x minus a times x minus b times x minus c times x minus d, we actually have x minus a times x minus a times x minus a, and so on. It repeats. What does that mean? How do we decompose that? Well, we write x minus a to the first power, and then we have a constant at the top, plus, and then the next to the denominator we have x minus a to the second, and then just a constant on top. And so on, we increase the exponents, but we still have constants on top because the denominators are linear, and we go all the way up to whatever exponent we have at the denominator. To exemplify this one, let's say if we have 3 over x plus 2 to the second power, then we would write it a over x plus 2 plus b over x plus 2 to the second. If I had to the third power, I would add plus c over x plus 2 to the third, and so on. Another type of partial fraction that we might encounter are terms where the denominator is quadratic. So if the denominator is quadratic, the expression that we would want to use would be keep the denominator and the numerator will be 1 power less, so it would be a linear one. So let's see how to use this in calculating integrals. So integral, let's look at this example that we have here. Integral of 3 over x minus 1 over x plus 2 dx. So if we take a look in the integration tables, we won't see any terms that have 1 over and then this type of product. If you can check through all this, you won't see a term like that. So that's why partial fractions are coming in handy. So let's take 3. 3 over x minus 1 times x plus 2. And let's break it down as we saw in the first type of problem. It's going to be a over x minus 1 plus b over x plus 2. So how do we decompose this, or how do we find, our goal now is to find a and b. We're going to multiply by x minus 1 times x plus 2 both sides, and we get 3 equals a times x plus 2, because when you multiply this one by x minus 1 times x plus 2, the x minus 1 with x minus 1 cancels, so we are left just with x plus 2. Plus b, and the same concept applies, and we have x minus 1 here. Now, we have more than one method to solve this. I'm going to use one method, and in a different problem, I'm going to use another one. If we set x equal to negative 2, we're going to get 3 on the left-hand side, and then this term here is going to be 0, and this term here is going to be negative 3b, so we'll be able to calculate b right away. So why did I choose negative 2? Because it's a 0 of these parentheses. Now if we choose x equals 1, we're going to get 3 equals 1 plus 2 is 3a, and then this term here is going to be 0. So a equals 1. So the choice that I made by choosing negative 2 and 1, or to eliminate one of the variables or one of the a or b and get this in a simpler form. So basically, our integral of 3 over x minus 1 times x plus 2 dx can be actually written as a over x minus 1, so 1 over x minus 1 integral of that dx, plus integral of b, which is negative 1 over x plus 2 dx. And if we take a look at these integrals, are much simpler to calculate. The first one is ln of absolute value of x minus 1. Let's bring this negative in front, so minus ln of absolute value of x plus 2 plus a constant, so I can actually use properties of logs and get ln of x minus 1 over x plus 2 plus c, and we actually solved the problem. Let's take a look at another example. Integral of x over x plus 3 to the second dx. Evaluate integral of x over x plus 3 to the second dx. We take this x over x plus 3 to the second and we decompose it into a over x plus 3 plus b over x plus 3 squared. We want to find a and b, so I'm going to multiply by x plus 3 squared both sides. And we get x equals a times, well, a over x plus 3 times x plus 3 squared, maybe I should show all work, plus b over x plus 3 squared times x plus 3 squared. This x plus 3 cancels with this and this with this. So we get x equals a times x plus 3 plus b. So I'm going to do the same way I did before. I set x equal to negative 3 and I'm going to get negative 3 and then plug it in this relation. So I get negative 3 equals, this quantity becomes 0, so I get equal to b. So b equals negative 3. Now there is no 0 that I should put here, so because of that I'm just going to set x equal to any value. Let's just choose 2. So we get, when we replace it in here, we get 2 equals a times 5 plus b, but b is negative 3. So if we solve this, we get 5 equals 5a, a equals 1. Which means our integral of x over x plus 3 squared dx can be actually written as a over x plus 3, which means integral of 1 over x plus 3 dx, and then b over that, so minus integral of 3 over x plus 3 squared dx. So let's solve this. The first integral is obviously ln of x plus 3, just right away. The second one I can actually put minus 3 integral of x plus 3 to the negative 2 dx. So I can use a substitution, u equals x plus 3, du equals dx. So our first integral, I'm just going to copy what I got, minus 3 integral of u to negative 2 du, which is a basic formula. So minus 3 u to negative 2 plus 1 over negative 2 plus 1. So we get ln of x plus 3 plus 3 u to negative 1, so over u, but u was x plus 3 plus c. Final answer. Now let's take a look at one more problem. Find the volume of the solid made when the region bounded by y equals x over x plus 1, the x-axis and x equals 4 is revolved by about x-axis. So I'm going to pause this and I'm going to make the graph, and then let's construct the integral that we need. So I sketched the graph. This is the y equals x over x plus 1. I gave values. This is x equals 4. This is the x-axis. So this is the solid. This is the region that we actually had to revolve. So we got this solid here. Now in order to find the volume, where we can use any of the methods that we learned, I'm going to use the disk method. So the volume is actually integral from 0 to 4, is pretty obvious from the graph, of And now if we want to find just the volume of one of these slices is actually the volume of a cylinder. So it's pi r squared. The radius is this distance, which is f of x squared dx. So in our case, it's going to be integral from 0 to 4. Pi times f of x, it's x over x plus 1 squared dx. So I would advise you to pause this and calculate the integral, and unpause and check if we got the same answers. So I noticed that the numerator and the denominator have the same power. So because of that, if we write them out, we'll use long division so that we can rewrite as quotient plus remainder over divisor. So then we end up with these two integrals that we can calculate using the tables. So in order to calculate the green integral, I use the substitution, u equals the denominator, and then du equals 2x plus 2. But the numerator, which we can see here, right, the numerator is negative 2x minus 1, so it's not 2x plus 2. So we'll do some math to actually write it in the way we want. So I actually broke down negative 2x minus 1 into this integral here, and then minus this integral here. So I broke the green one into two blue ones. So now we get pi 4 minus 0 minus. Now the denominator, if we differentiate it with, we'll need a plus 2, but then a minus 2. So then the integral becomes integral from 0 to 4, 2x plus 2 over x squared plus 2x plus 1 dx. And then minus with minus 2 would be plus 2 integral from 0 to 4 of dx over x squared plus 2x plus 1 dx. And then minus the same thing. So 2 minus 1 is going to be 1. So I'm just going to leave it like this. So we get pi times 4 minus, now this is u and this is du, so it's going to be ln of absolute value of x squared plus 2x plus 1 evaluated from 0 to 4, and then this one I can actually write integral from 0 to 4 of x plus 1. It would be squared at the denominator, so minus 2, because I can calculate it right away. So we get pi times 4 minus ln of 16 plus 8, 24, 25, minus ln of 1, which is 0, plus, and this one is x plus 1 to negative 2 plus 1 over negative 2 plus 1, so it's minus 1 over x plus 1 evaluated from 0 to 4. So we get pi times 4 minus ln of 25 minus 1 over 5 plus 1. A little bit of algebra, so 4 plus 1, 5. So pi times 5 minus 1/5 is 24 over 5 minus ln of 25, and we solve the problem.